So welcome to the 20th lecture of surface engineering. We are still discussing some of the fundamental aspects. We did discuss quite a bit of it already about structures, about microstructural evolution, defects, and then various forms of engineering properties related to the surface. We classified them into mechanical, chemical, and physical properties. We also discussed various approaches of surface engineering. We classified them into three possible categories. And then at the moment we would like to take up discussion on one of the most important engineering solid that is used for various kinds of structural applications, meaning where mechanical behavior and performance under various kinds of loads and rate of loading matter. I'm talking about steel, and in fact, if you look at the very first view graph, this is a very well-known phase diagram, which is essentially an equilibrium diagram, but for a difference, to be more precise, this is a metastable equilibrium diagram, because we're dealing with iron cementite, where cementite is not truly an equilibrium product. But for all practical purposes, because cementite doesn't transform at room temperature, we consider this to be as good as a phase diagram or an equilibrium phase diagram. Now, why is steel so important? I did allude to that in the last lecture, and let me repeat that this is the tonnage-wise, this is the second most important engineering material for all kinds of structural applications, starting from construction to various bodies and various tooling and manufacturing applications. The first question is that why is steel so versatile? The main reason lies in the fact that when you talk of steel, you actually first have to realize that we are talking about a binary where one part is iron and the other part is cementite. So actually the diagram should have ended at 100%, but this is only up to 6.67%, meaning this is actually 100% of cementite. Now, on the other side, of course, we have pure iron. And we can easily see that after solidification at this melting temperature, pure iron undergoes three very major allotropic transformations. So from delta iron to gamma iron. So this is the part when steel or iron, pure iron, exists only in the form of FCC variety, which is called gamma iron, and then subsequently it transforms to beta and then to alpha, and the transformation across the Curie temperature, which is typically about 768 degrees centigrade, is only associated with a paramagnetic to ferromagnetic transformation without any change in crystal structure. So BCC, FCC, then again BCC. And this is very unusual because usually for all metallic systems at room temperature, you would expect the closed packed structure to be stable. In that, by going by that logic, one should have expected FCC to continue until room temperature. But because of a very specific pattern of variation of specific heat as a function of temperature for the two crystallographic varieties or crystal systems, variation of two crystal systems, which essentially could look like this. So it is because of this variation of the two varieties of the crystal lattices of iron, pure iron, as a function of temperature, we see that if this is the BCC phase, if this is the BCC phase, and if this is the FCC phase, then, if this is the FCC phase, then we realize that in this temperature range, we see FCC to be stable and in this range and in this range the BCC phase to be stable, because Cp is lower, and accordingly the stability of the phase depends upon the contribution of Cp to enthalpy and entropy. In other words, this is the temperature range. So we see a variation of the crystal structure of pure iron going from BCC to FCC and then FCC to BCC. So this kind of crystallographic transformations of pure iron allows a large number of phase transformations to occur in steel, and because of this possibility we see a very large variation of crystallographic forms, and hence large variation of properties. We also see that steel will have certain transformations which are called invariant transformations, and these invariant transformations are dictated by the Gibbs phase rule, which says the degree of freedom is given by a relationship which says the degree of freedom, is equal to the number of components present plus 1, which represents here only the temperature, but actually it can be 2 if it's a non-condensed system where both influences of temperature and pressure are important. But for all condensed systems, only temperature matters, variation of temperature matters. So C plus 1 minus the number of phases present. So since this is a binary, so since we are talking about binary, so obviously wherever we have 3 phases coexisting, for example, at this eutectic point or at this peritectic point or at this eutectoid point, we have a situation which is called invariant. And as a result, we see a transformation where, for example, here liquid, then gamma and Fe3C should be simultaneously present. So these invariant transformations, this is not of much use because this is at a high temperature involving a liquid. This certainly has a wide range of applications because it allows the fusion temperature to be drastically decreased from over 1500 or larger to very low temperature. So it makes casting very easy. So this varieties of iron carbon or iron cementite system is called cast iron, and the name cast iron essentially is derived mainly to signify that casting is very much conducive at this low melting alloys. But the difference between cast iron and steel is not necessarily only in terms of composition, but essentially in terms of this particular horizontal called eutectic isotherm. So any composition which intersects this eutectic isotherm is called cast iron, and the remaining are essentially called steel. But in plain carbon steel or plain carbon system without much of alloying elements, typically this boundary is at about 2% of carbon. Now coming to the main issue as to why steel is so important, as we said that the specific heat is going to be the factor which determines whether we have what crystallographic form of iron is present, and this kind of transformations called the allotropic transformation, which are reversible transformations of pure elements from one particular crystal form to another. So because of the presence of these kind of allotropic changes 1, 2, 3 and 4 until room temperature for pure iron, we see a wide variation of properties possible in this steel. We'll elaborate more as we go along. So what is important is that at room temperature, the phase aggregate that we see can be widely varied as we cool from liquid state to lower temperature. So when the phase aggregates change, the microstructure changes, and when the microstructure changes, the properties change. For the steel part, the most important transformation is this Eutectoid change. And this Eutectoid change essentially means when gamma transforms, should simultaneously transforms to ferrite and cementite. Now this is a solid solution and this is an interstitial compound. The combination of this very hard phase with relatively softer matrix gives you a product solid at the end, which can actually be varied in terms of its mechanical properties over a wide range. And this is exactly the reason why steel is so versatile. So here is an alloy which in solid state can give you mechanical strength anywhere from few hundred to over 1000 megapascal. Here is an alloy which can give you ductility as low as a few percent to close to 100% depending on the typical microstructural state we are talking about. In particular, steel also is one of the very rare alloys which apart from showing large variations of mechanical strength can also provide us a very high amount of toughness. So combination of strength and toughness is what makes steel so versatile for various kinds of structural applications. So now we need to move on and understand as to what are the possible variations of steel microstructure that makes it so versatile. So if you look at, we first saw the phase diagram, and as I mentioned, it's essentially an equilibrium diagram which only talks about the existence of phases and phase aggregates depending upon the temperature and composition variation or combination. But then when you are talking about a transformation, you bring in the kinetic factor, which means you now need to invoke the idea of how does the microstructure change with time. So whenever you bring in the need to bring in time component, so you have to now talk about the so-called kinetic diagrams. And here's a kinetic diagram which is nothing but a temperature time. So variation of essentially variation when you are varying temperature and time independently, how does the microstructure change? And this is basically explained in terms of certain boundary of transformations. For example, this is one curve which actually shows the beginning of a particular type of transformation. This is the other end, which is the end of such a transformation. And the transformation that we are talking about is essentially the Eutectoid transformation, which we just heard as a transformation which involves transformation of austenite, which is an FCC solid solution of interstitial carbon in gamma iron, into BCC ferrite and cementite. So this is Eutectoid transformation. But this Eutectoid transformation, depending upon where it is actually intersecting the beginning and the end, for example, if the intersection of the time temperature plot is somewhat like this, then you end up getting a microstructure which is perlitic, where we have alternate sequence of cementite and these bright regions are ferrite. So we have cementite and two cementite, and in between the bright regions are ferrite. So this lamellar alternated structure gives us one set of properties which actually is a very nice combination of strength and ductility. And this is called pearlite because this morphology resembles the mother of pearl. Just as you see the shell, this morphology is contour wise very similar to that. So that's where the name is derived from. But instead of cooling at this rate, if you happen to cool, for example, in a stepped manner like this, then you're likely to see another transformation product, essentially the same Eutectoid transformation, same invariant transformation, but the phase aggregate, the mechanism, and the sequence of evolution of the phases and their volume fraction distribution is different because the mechanism of transformation is different. And that aggregate is called bainite. The interesting fact here is that we are talking about two aggregates, pearlite and bainite, which are nothing but the phase aggregates. The difference lies primarily in terms of the appearance or the microstructure, but also in the mechanism. In case of pearlite, usually cementite nucleates first. So essentially, if you are talking about two grains, so if this is the prior austenitic microstructure, all grains are gamma or austenite. So on this boundary, you would first happen to see certain nucleation of cementite, and this kind of a boundary will tend to move when you form such cementite lamellae, and when they actually grow edgewise, simultaneously the portion in between transforms to ferrite. So nucleation of cementite triggering formation of ferrite because of carbon depletion. So this is how we end up getting such lamellar aggregate, where the volume fraction of this aggregate is purely dictated by the phase diagram. On the other hand, when we talk of bainite, which essentially forms at a much lower temperature, and because of lower temperature, now we are talking about a much larger undercooling and hence much greater driving force. So under this larger driving force, when the transformation begins and ends at a lower temperature, we end up getting a microstructure where, for a difference, the ferritic sheaves nucleate first. So essentially you'll see such sheaf-like structure of just like leaf. So these are like palm leaf type of a structure, and when such a ferritic sheaf nucleates, the excess carbon is rejected, and those excess carbons nucleate as small stringers or platelets in the form of platelets, either between two such consecutive sheaves or embedded within the sheaves. So accordingly we get sort of upper and lower bainite. So what is important for us to know is that if the microstructure changes from such pure lamellar alternate sequence of ferrite cementite to a situation where we have broad leaf or sheaf kind of a structure of ferrite within which cementite is embedded, we end up getting fairly different kind of properties. In fact, we'll come to that in a minute. So from equilibrium diagram, what we earlier saw, so from this equilibrium diagram wherein we saw, so while talking about this steel part of the diagram, what we have seen is that this is the portion which is very, very important for us, because from a single phase we are going into a two-phase aggregate, and the way the two phases manifest themselves or present themselves in the microstructure makes it possible to call it pearlite or bainite. And because of these two aggregates, different types of aggregates which arise or emerge because of two different mechanisms of transformations, we actually see two different types of microstructures. We'll talk about bainite later. Now the next question is to be now, to make things even more clearer, we actually need to follow this microstructural evolution a little bit more. But before we do that, I must tell you that this kind of a kinetic diagram that we are seeing here, so this kinetic diagram of essentially time temperature plot is typical of plain carbon steel. And the difference here, what is important noting at this point, is that this region is the so-called knee region. This is where, just like the knee of our leg is a joint between the upper and the lower part of the limb, and if this is the portion where it bends, and this is where it comes closest to the temperature axis, or in other words, this is the limit defined, time limit defined, which is important if we want to avoid intersecting any of these curves. So if I need to intersect the start line or the curve which is designating the starting of the pearlitic or bainitic transformations, then I need to employ a cooling rate which is very, very fast. So our ability to avoid intersecting any of these lines will be determined by the gap between the temperature axis and the tip of this knee, and this is called critical cooling rate. For various transformations, particularly for martensitic transformations, we would like to have a situation where this knee portion is actually shifted to the right. And if we can shift it way to the right, then I can afford to cool fairly slow instead of so fast, and yet be able to avoid the start of these pearlitic or bainitic transformations and then intersect the martensitic line, which is way below, easily. And if I cool slow, the advantage is that I incur less or least amount of thermal shock, because I'm cooling all the way from above 800 to room temperature. So this 800 degree of gradient is large if we need to cool within a few seconds or less than a second. So the cooling rate we are talking about is actually a few hundred centigrades per second. So in order to make life easier, to be able to not only avoid the intersection with this pearlitic or bainitic parts, also if we want similar slow cooling somewhat like this, where I can take life easy and cool slowly like this and get pearlite. If I cool slightly faster, then I actually can get into bainite and make full bainitic microstructure. And if otherwise, if I cool even not as slow as this, but fairly slow, and still if I am able to make if I am able to avoid both initiation of pearlitic or bainitic transformation and still end up getting complete martensite, that's also possible. So simply by varying the cooling rates from 1 to 2 to 3, I'm able to vary the microstructure over a wide range. And this is exactly the reason why steel is the most versatile structural material for all kinds of structural applications. So to be able to understand as to why this is happening, we must be able to appreciate both the varieties or the information available in the phase diagram and also the application of such kinetic diagrams. But there's one important part which I haven't talked about, and that is how do we change the shape and the contour of such a kinetic diagram from this fairly start and finish, so exactly from this kind of a manifestation to somewhat a different kind of a shape which is very convenient to me. So I have split this curve and this curve into 1, 2 and a line. So instead of having a diagram like this, which essentially by the way is called the TTT diagram, time temperature transformation diagram, but here the cooling is isothermal. But instead of time temperature transformation, if we want to refer to continuous cooling, then we have slight variation of these diagrams. Through some kinetic analysis, we can actually transform this TTT into continuous cooling transformation diagram, and then we can apply this kind of continuous cooling curves and then predict what kind of a microstructure we are going to get. So the point I'm trying to make is that if I want this change in shape of this kind of a TTT or CCT into such split portions, so instead of having such a kind of a curve situation, if we want to split and split such a way either like this, so this portion is pearlite and this portion is bainite. So in order to split the two curves like this or completely have two different curves for pearlite and bainite, we need to bring in another influence, and that influence is coming from the so-called alloying elements. So if I alloy the steel with various kinds of alloying elements, and in fact the alloying elements can be of three types. One set of elements which stabilize ferrite, we call them ferrite stabilizers. Another form which stabilizes gamma or austenite, we call them austenite stabilizers. And another form which actually stabilizes or has a large tendency for formation of carbides. This is proving little difficult for me to write on this board. Anyway, so the point I'm trying to make is that all elements usually which are BCC in terms of their Brava lattices, they are usually the ferrite stabilizers. Alloying elements which carry FCC crystal structure or Brava lattice are usually the austenite stabilizers. And there are elements both coming from BCC and FCC varieties, but usually the BCC ones, which have a large tendency for the formation of various kinds of carbides, like for example titanium or tungsten and so on, though this is HCP and this is BCC, but they have a very high affinity for carbon, and when they combine with carbon they form these carbides. So playing with the composition by adding ferrite stabilizer or austenite stabilizers, we can shift the contour of not only the kinetic diagram but actually the phase diagram, and from the phase diagram we can also derive the various differences that are possible for such kinetic diagrams. So splitting of these curves and giving space in between so that I can cool slowly and then much easily derive the microstructures which are pearlitic or benitic or martensitic in nature, that's quite possible by using such the influence of alloying elements. But even for the same steel, if I am not willing to change the composition, if I am not actually going to have variations or addition of various alloying elements, for the same steel which I alluded right in the beginning, I can cool relatively slow, slightly faster, still faster, and much faster, and the fastest. So by way of employing different kinds of cooling rates, I actually can get coarse pearlitic microstructure, fine pearlitic microstructure, combination of martensite and pearlite, and then finally full martensitic microstructure. So such wide variation of microstructure is possible on the same steel in the similar setup, but simply by employing different kinds of cooling rates. And this kind of variation of cooling rates essentially are kinetic intervention onto the same alloy, giving rise to such differences in micro aggregates or phase aggregate, and as a result the composition can very significantly vary. So one thing which I didn't quite mention is the fact that when we talk of all these transformations, these are all transformations happening on cooling. But if you look at this phase diagram, we must begin from a similar level playing ground, and that is austenite. So in order to create this, go into this austenite phase first for any transformation, before we actually think of any such transformation, we must read this or understand this kinetic diagram again very carefully. And this is a kinetic diagram with a difference, because here what we are saying is that if you start from this point, which is essentially the room temperature point, and this is the starting point. So in terms of temperature and time, this is the starting point. So if you heat in these two possible modes, then you realize that in order to reach homogeneous austenite state, you require much larger time. On the other hand, if you are actually willing to heat to higher temperature, so if the temperature is low, then we need to heat for longer period of time or hold for longer period of time. If we are willing to heat to higher temperature, then at a much, so if we are willing to heat to higher temperature, we may expect to reach homogeneous austenite state at a much lower time frame. So it is important for us, before we begin any such transformation, to make sure that the austenite is single phase. So the microstructure will be such single phase microstructure, all austenite, and all exactly of the same composition. So homogeneous both in terms of microstructure and composition. Then only on cooling, whatever microstructure you develop will be reproducible, precise, and give you the same set of properties that you want. So this is something which we have discussed earlier, but I thought I would just touch upon it once more to tell you that when we talk of various forms, or particularly two major forms of iron, pure iron, namely the BCC at room temperature and FCC at high temperature. So in these two varieties, the unit cell, which is the smallest building block for any Bravais lattice or crystal structure for that matter, allows us to calculate the typical size of the void. So, in case of FCC, this is how we can calculate the size of the void, and if this is the diameter of the iron atom in the BCC form, this is how one can calculate the tetrahedral or the octahedral void size for BCC iron. Similarly, for FCC, we can calculate the tetrahedral and the octahedral, I'm sorry, this should be the octahedral void size for carbon or any other interstitial atom to come and squeeze in. This is important for us to know because this size, relative sizes of these interstitial voids essentially determines what will be the solubility of such interstitial atoms. When I was referring to alloying elements, I should have mentioned that principally the alloying elements will actually they'll be of two types. One is the so-called interstitial and the other one is substitutional. The interstitial ones are the ones which can squeeze into these holes, but these sizes of these holes are actually always smaller than the even the smallest possible atom one can think of. So, whenever we push in such interstitial atom, there will be a lot of strain field around that, and because of which solubility is limited. So, the solubility part is primarily, particularly in case with regard to steel, is determined by the so-called interstitial void sizes, and it is because of this reason you can pack in always more amount of carbon in FCC variety than in BCC. But on the other hand, the voids in the BCC are interconnected, and it is because of this reason that the carbon diffuses faster in the BCC variety than in FCC variety. So, solubility is higher in FCC, but diffusivity is higher in BCC, and both these properties are very important in terms of determining whether for various kinds of phase transformations and phase aggregates that we want to bring in. So, so this is what I was trying to say, that if you bring in different kinds of phase aggregates, for example, when you have pearlitic aggregate or behnitic aggregate, this is the strength properties and this is the hardness properties in terms of the Rockwell scale. So, the temperature scale here is somewhat similar to the temperature scale that you see in the TTT diagram, and what it shows is that if you start from this end, that means if you actually allow the transformation to take place at relatively high temperature, so somewhere let's say in this region or in this region. So, this is how the temperature is decreasing, and as the temperature decreases, what we see is that the strength properties, both in terms of hardness or yield strength or any other strength representations, will always show you higher and higher value. So, given a choice, if you are looking for very high hardness or very high strength for that matter, then obviously you would prefer to have a behnitic microstructure than pearlitic microstructure. But the problem is that in case of plain carbon steel, because of the nature or the curvature of this TTT or the CCT diagram, and the cooling rate obviously is going to have slightly just the opposite kind of a curvature. So, two curves of opposite curvatures can intersect only once and not twice. I mean, it can be tangential at the most, but you cannot, using another kind of a cooling curve with a different curvature, there is no way this curve can actually intersect the other curve with a different opposite curvature at a portion below the knee, below the tip of the curvature. So, you need a stepped quenching. In other words, if you want bainite, then you cannot employ a continuous cooling like you can do for pearlite. You have to do a stepped cooling, and this stepped cooling kind of a transformation is called austempering, and so it's called austempering, and this austempering is a heat treatment which requires such stepped cooling. So in order to get higher strength properties like here, we actually need to allow the transformation to take place at lower temperatures, and such transformation is possible not by continuous cooling but by stepped cooling. So, with this, now we actually would like to summarize, and as a way of recapitulation, what we have understood in this discourse is what is iron cementite diagram, and I didn't quite mention, but it's for you to make out the difference between the so-called precise equilibrium diagram, which is called iron carbon, or in some cases called iron graphite diagram, because graphite is the stablest form of carbon in steel. So the differences will be in terms of the composition of the invariant transformations and their the isothermal temperatures where actually these transformations are happening. So we talked about various invariant transformations. In fact, all the allotropic changes, the two melting of the two components, and then the three invariant transformations, peritectic, eutectic, and eutectoid. All these are invariant transformations, and they are very important because they determine the microstructural evolution of the alloys, not of the pure iron or pure cementite. We understood that the ability to vary the properties, namely the mechanical properties of steel, which is what makes it so versatile, is possible purely because of the ability to vary the microstructure over a very wide range. And this is not quite possible in almost all types of other metallic or non-metallic systems or alloys. We understood the difference between the evolution of pearlite and bainite, primarily in terms of the temperature range where it happens, the morphologies of the phases, and most importantly the mechanism as to what nucleates and what promotes the formation of the counterpart. So it's in case of pearlite, cementite, leading to formation of ferrite. In case of bainite, it's actually because of large undercooling. It's first ferrite and followed by nucleation of cementite. Of course, there is some amount of controversy existing about exact mechanism, whether it's a diffusional or there is a non-diffusional component, but that's a different subject altogether. We also saw how the interstitial void sizes are different in FCC and BCC form of iron, and which is why the solubilities are different in these two forms of iron and alloys. The most important thing is that we need to understand the difference between the phase diagrams or the equilibrium diagrams and kinetic diagrams. For example, when we talk of solubility, you certainly refer to thermodynamic diagram. When you talk of evolution of phase aggregate or the rate at which they appear, you have to refer to a kinetic diagram. So the last thing that I need to mention is that we talked entirely about the bulk of the steel. All these discussions are related to the bulk of the steel. And when we go to the next lecture, we'll realize as to why it is important for us to appreciate what happens in the bulk of the steel, even though this particular entire discussion is related to a course called surface engineering. Okay, thank you very much.